The last thing we're going to do before we're going to kind of go back to graphing is, instead of algebra of functions, we're going to do something called composition of functions. Now, composition of functions is something that can totally be useful. Now, whether this will make any sense to you or not, this is my attempt at being like, hey, look at it in practice. So what it is that we could look at a temperature example. So for example, if I wanted to convert from Fahrenheit to Celsius, I could use this formula. So to convert to Celsius, you do 5/9 times the Fahrenheit temperature minus 32. Great. Well, there's another temperature scale that if you're taking chemistry specifically, you might talk about a bit in physics, but there's something called the kelvins. And you can convert from Celsius to kelvins really simply. To find kelvins, you take a Celsius temperature and add 273. Well, what if I wanted to convert from Fahrenheit to kelvins? So I have an equation from Fahrenheit to Celsius. I have an equation from Celsius to kelvins, but if I want to go from Fahrenheit to kelvins, I could use a composition of functions to get there. In other words, if I wanted to find kelvins from Fahrenheit, I could substitute in the expression for finding Celsius from Fahrenheit, and then I could have a new function. So in other words, if I want to try to find kelvins, I can find Celsius in terms of Fahrenheit. So instead of putting Celsius in here, I'm going to put Celsius in terms of Fahrenheit. And so everywhere that there's a Celsius measurement, I'm going to put in the formula for Celsius converting from Fahrenheit, which will come up with a new equation, kelvins in terms of Fahrenheit, which would be 5/9 times F, or Fahrenheit minus 32 plus 273. And I've come up with this new composition function, which came from putting an equation for something else into an equation for something else. Okay, maybe that helps make you feel like you want to do it. Maybe you're just more confused. And if you're more confused, just ignore what I just said and let's just do it. So, composition of functions. Composition of functions is different than multiplying functions. So multiplying, when I want you to multiply, the function notation would be f at x, okay, or f, I guess I should put a g to make it the same as the bottom of the bottom, other one below it. So fg at x. This means multiply. This means composition. So when you have the open circle between the f and the g, it means that you're going to compose the two functions. You're going to plug one into the other. In fact, whatever one's written second is getting plugged into the function that's written first. So in other words, we're putting the g of x equation into the f of x equation. If it was g of f of x, then you would be plugging the f of x equation into the g of x equation. Okay, so composition is read like you do the O as an of. So f of g of x is how this is written. That looks horrible, hey? So it's f of g of x. The important thing is that we're going to talk about domains. And the domain of g of x will be included in the new domain of f of g of x, but I'll explain that as we go. All right, let's look at a simple example to start with. I've got a function defined by 4x plus 1 and a function defined as 5x. First off, let's talk about domains. The domains of each of these is negative infinity to infinity. So no matter what, when I do a composition of functions, the new domain will be negative infinity to infinity because none of the composition involves making something be a division. So we can kind of ignore domain in this example and then we'll focus on it in the other ones. But let's see what this means. So this wants me to do f of g of x. In other words, it wants me to plug the g of x equation in for x in the f of x equation. It sounds horribly complicated, but let's just say that I'm plugging into the f of x equation. I'm plugging into 4, I'm going to replace the x with a bracket, plus 1. So I'm plugging into the f of x equation. Now what am I plugging in? Well, I'm plugging in the g of x equation, which is 5x. So in for x in the f of x equation, I'm going to put the g of x expression, which is 5x. So everywhere there was an x, I'm going to put 5x, and that's it. So this gives me 20x plus 1. The domain, like I said in the beginning, because my original domains were negative infinity to infinity, this domain is going to be negative infinity to infinity. It won't change. Okay, so then I could ask you to do something like find f of g at 2. And so you would do 20 times 2 plus 1, which gives you 41. Now, for some people, they're like, I don't really get it. So let me try in a different way. What if I said to find f of g at 2? Let's say we hadn't done this part. Let's say I wanted to find f at g at 2. So let's say I took it first and I said, well, what is g at 2? Well, g at 2 is 5 times 2, which is 10. Okay, so that's the value of g at 2. Now what I'd want to do is plug in for g at 2, I would plug a 10 into my f of x equation. So I had to solve something so that I could then put that into the next equation. It's like up here. I would have to solve for the kelvins and then put the kelvins, or sorry, I'd have to solve for Celsius and then put the Celsius into the kelvins formula. Right? So this is kind of doing like what I'm doing right now is going from here to here to here versus going from Celsius all the way, or sorry, Fahrenheit all the way to Kelvins, right? I wish I had you guys to nod at me and be like, oh yeah, I get it. Or maybe you're just all looking at the screen being like, what is she talking about? Right? So this one is like me saying, hey, I'm starting in Fahrenheit, go straight to Kelvins. This is me saying, hey, I'm going to go from Fahrenheit to Celsius. Then I'm going to put in the Celsius and convert to kelvins. So now I would put 10 in for x in my f of x equation, and I get 41. So I get the same answer no matter which way I did it. And maybe that helps you understand it. Maybe it doesn't. Maybe we should chat and see if we can get you to get it. All right, so I'd like you to pause the video and try g at f of x. So give this one a go. See if you can plug the f of x equation into the g of x equation, figure out what the new domain is, and then plug in the value of 2. So for me, I like to write it like this first. In fact, I like to say, well, what is f of x? What am I plugging into the g of x equation? Okay, I'm plugging 4x plus 1 into the g of x equation. Well, what's the g of x equation? The g of x equation is 5 times x. Everywhere there's an x, I'm going to put 4x plus 1. So I get 20x plus 5. Now, domain, don't let me forget that. Right? These ones, it won't change. It's always going to be negative infinity to infinity, which you can tell here. There's no denominators, no radicals. There was no denominators and radicals in my beginning expressions. Okay, and then I want to find g at f at 2. So I'm going to simply, because I've done it, plug it into my g at f of x equation. So I get 20 times 2 plus 5, which is 45. But again, I could have plugged in x is 2 into my f of x equation, right? And gotten 4 times 2 plus 1 is 9. And then I could have plugged 9 into my g of x equation and gotten 5 times 9 is 45. Blasted. 45. There we go. I don't know why it does it. My pen drags on the 4s and y's. Okay, I'm going to make that one a 4 in case you're reading it later. Okay. Now let's move on to making the expressions a little bit more complicated. So let's throw in some radicals and see what happens to our domain. So my f of x equation, my domain of my f of x equation would be that x has to be greater than or equal to 0, right? But I should probably put that as integral notation. That's hard to train me out of this. So 0 to infinity. Okay. For this one, the g of x equation, because there's no denominators, there's no radicals, my domain is negative infinity to infinity. Okay, so now let's see what happens when we do a composition of functions. So I want to find f at g at x. In other words, I want to plug the g of x equation into the f of x equation. Now my g of x equation is 4 minus 2x. I'll talk about domain after. Let's just keep going. So now into my f of x equation, which is the square root of x, I'm going to replace x with 4 minus 2x. Now I replaced it in a bracket. I didn't need the bracket. I'm just going to leave it like this. Okay, when you're talking about domain, because we're inserting the g of x equation, the g of x domain will be included in my final domain. Okay, so the 4 minus 2x, because it's getting plugged into the other equation, the 4 minus 2x isn't getting changed, whereas the square root of x is getting changed. So this domain for this guy doesn't get included, but the g of x domain does. Okay, which is just negative infinity to infinity. Then I have to go to the bottom and I'm going to get a new domain. So when you're doing composition of functions, it's a little different than algebra. Algebra, you kind of, well, actually algebra, you still needed a new domain when we did division, but you're always going to have to come up with a new domain with composition of functions, okay? But you also always have to include the original domain of whatever's getting plugged in. So the g of x domain is getting plugged in, it stays. Then we have to find a new domain for my finished function. Because it has a square root, it is going to have a domain restriction. So 4 minus 2x has to be greater than or equal to 0. Now you can either add 2x if you don't want to flip your inequality sign, or move everything over. I'm going to add the 2x because I think last time I did it the other way. So I'm going to add 2x to both sides. I get 4 is greater than or equal to 2x. Then I'm going to divide by positive 2 so I don't have to flip my sign. And I get x is less than or equal to 2. In interval notation, right, x is less than or equal to 2. In interval notation, that is negative infinity. 2 down to negative infinity. This is my new domain. It has to include my old domain, which isn't going to restrict it at all, so that I could say that my final domain is just negative 2 down to negative infinity. Yeah? Let's try another one. So what if I wanted to find g of x? So this time I'm plugging my g of x equation into my g of x equation. I'm plugging it into itself, which is super weird, but it happens. So I'm going to plug the g of x equation into the g of x equation. In other words, into the g of x equation, I'm going to put in 4 minus 2x. Now at this point, I'm going to keep track of my domain. The domain of this function is negative infinity to infinity. Then I'm going to plug that into my g of x equation. So my g of x equation is 4 minus 2x. In for the x, I'm going to put 4 minus 2x. Then I'm going to simplify. I get 4 minus 8 plus 4x, which gives me 4x minus 4. Now I check for my new domain, which because there's no radicals or denominators is still negative infinity to infinity. So I include the old domain plus, or the inputted domain plus the new domain, and I can say that my overall domain is negative infinity to infinity. Okay. Moving on to the last one. This one is probably the most complicated. So if you need to pause the video and take a break before we do this one, feel free. But what we're going to do is we are going to do f of g of x and g of f of x and do the domain of each. So let's start with f of g of x. And you'll notice they get even lazier. They stop writing the of x and they assume that you're going to do a composition of f of g of x. Okay, so for this one, I'm plugging in to the f of x equation, I'm plugging in the g of x equation. So into the f of x equation, I'm going to put in 5 over x. And I'm going to look at my domain right now. So my domain of this g of x function, which is getting inputted, is that x cannot equal 0 because my denominator cannot equal 0. Okay, so this is my domain here and it's sticking. Then I'm going to do my composition of functions. So I'm going to take my 1 over x minus 2, which is my f of x equation, and in for x, I'm going to put 5 over x. Okay, now I'm going to simplify. Now this is something that you might not have done since Math 50, or if you didn't take Math 50, you might have done it for a while. But how do I deal with what this is called a complex or a compound fraction? In other words, a fraction inside of a fraction. I'm going to show you 2 ways of dealing with this, and you can decide which one you like the best. Way number 1, if you've had me as an instructor before, I'm a creationist or a destructionist. So I'll teach you first the creation way. The creation way is that this is my numerator, 1, is getting divided by my denominator, 5 over x minus 2. So I've changed it to a division of fractions. Now to divide fractions, you have to flip the second fraction and multiply. But this isn't a fraction, this is 2 fractions. So the first thing I have to do is create a common denominator. So I'm going to give this guy a denominator of x by multiplying by x over x, and I get 5 minus 2x all over x. Now I have a single fraction that I can flip, so I'm going to change it to multiplication and say this is 1 or x over 5 minus 2x, and then I'm going to multiply. So that leaves me with x over 5 minus 2x, because anything times by 1 doesn't change. Okay, this is my, f of g? This is my f of g. But I want to talk about the domain. I need to talk about the domain of this new function. My new function has a denominator, which is 5 minus 2x. which cannot equal 0. So let's solve this new domain. I'm going to minus 5. Actually, I'm going to just add 2x. I'm going to add 2x. I get 5 cannot equal 2x. And then I'm going to divide by 2. And I get x cannot equal 5 halves. This is my new domain. And even though your original domain no longer exists, it still counts, because this is technically f of g of x, but we've simplified it. So since this is my original function, the domain still has to count. X still cannot equal 0. So my final domain would be that x cannot equal 0 or 5 halves. And I think our textbook likes to go like this. It's the set of x such that x cannot equal 0 or 5 halves. Or interval notation, you can go negative infinity up to 0, 0 up to 5 halves, and then 5 halves up to infinity. All right, now I totally forgot I was going to talk about a different way to simplify this compound fraction. So if you didn't like this, maybe you're a destroyer. If you're a destroyer, so this is method number 1, this is method number 2. If you're a destroyer, you have 1 over 5x minus 2. And what we want to do is destroy the denominator. So the rule is you're allowed to multiply anything you want by 1. So I can multiply this fraction by 1, no problem, won't change its identity. But there'd be no point in multiplying by 1. What you're going to do is multiply by the lowest common denominator, which the only denominator is an x. So I'm going to multiply top and bottom by x over x. What that's going to leave me with is x times 1 over 5 divided by x times x. I'm multiplying every term in the denominator by x and every term in the numerator by x. So that's going to leave me with an x in the numerator. Now the whole reason you multiply the lowest common denominator is so that your denominator goes x divided by x is gone, and I'm left with 5 minus 2x. So again, two methods. I call this one the creation method because you have to create a common denominator, flip and multiply. And then I call the second one the destruction method because you destroy all denominators that are compound and then you end up. But we got the same answer. And no matter what, my new domain is x cannot equal to 5 halves. Don't forget the 0, and then you get your new domain. Okay, maybe you feel up to it, maybe you don't. But I'd like you to try g of f of x. So if you feel up to it, now would be a great time to pause the video and give this one a go. Okay, so if you didn't pause the video, or even if you did, here we go. We've got g at f at x. So I'm plugging the f of x equation into the g of x equation. Now the f of x equation is 1 over x minus 2. I'm going to find its domain right now. So the domain right now, again, your denominator cannot equal 0. So x cannot equal 2. All right, that's going to stay no matter what because that's going to get put in. Now I'm going to plug that into my g of x equation. My g of x equation is 5 over x, and I'm going to replace the x with 1 over x minus 2. And this is my function, right? This is g of f of x. And so that's why x cannot equal 2. But now let's simplify this. Now this one you could multiply top and bottom by x minus 2 over x minus 2, but this one's set up perfectly to be like 5 divided by 1 over x minus 2. It's already a single fraction. So I'll go 5 times x minus 2 over 1, which leaves me with 5 times x minus 2, which is 5x minus 10. So the new domain is everything's okay, right? Totally fine. There's no denominators, there's no radicals. But I have to include the original domain. So even though my new function, my new g of f of x, doesn't appear to have any domain restrictions, it is a simplified version of this. So we have to include our original domain restriction. So again, in set notation, I could say it's the set of x such that x does not equal 2. Or in interval notation, I could say negative infinity up to 2, and then 2 up to infinity. All right, hopefully that feels okay. Let me know if you have any questions. Go and try the quick check, and then we'll go move on.